Hello, I am Shinji Hoshino from Tokyo Institute of Technology, and I'll be presenting STRAB. The goal of STRAB is to reverse debug deployed concurrent programs. And you want to achieve this without architecture dependence. The problem with achieving this goal is that while trying to achieve architecture independence, we've used reverse execution at intermediate representation IR level, but this has decreased the recovery rate compared to machine level reverse executions. So our solution is to increase the recovery rate by using a novel hybrid memory location resolution, and also some supporting methods of lifting machine level information in the core dump into IR level. As a result, compared to the state-of-art reverse debugger repeat, we have increased the recovery rate by 40% on average, and while only being 2.7 times slower on real-world C concurrent programs. We'll now explain the goal in more detail. So what is reverse debugging? So here is a concurrent program which is deployed. If a deployed concurrent program fails, well, it is very easy to obtain the core dump. However, because the execution of a concurrent program is usually non-deterministic, it is hard to infer what happened before the crash. The core dump is basically a snapshot when the program crashed, but we cannot easily recover the states right before the crash. The reverse debugger is a tool that recovers the states before the crash, helping the developer to determine the root cause of the crash. And our goal here is to achieve this without depending on architecture, well, more specifically, hardware trace technologies. So an existing method called repeat uses hardware technologies such as Intel PT in order to enrich the core dump with trace information. Well, more precisely, this trace information is this trace information allows repeat to serialize the whole execution from the enriched core dump. And in this serialized execution path, repeat reverse execute and forward executes, well, repeatedly to recover program states before the crash. And this is done at machine level. Today, we present repeat STRAB, which focuses on the reverse and forward execution. So the problem here is that while trying to achieve architecture independence, the first step we took was that we wanted to do the reverse and forward execution at more abstract levels, precisely LLVM IR. But the problem we faced is that IR does some abstraction that causes repeat to have much lower recovery rate than well expected. Well, the main reason for this is that repeat, in order to achieve very high recovery speed, they decided that they will only use concrete values for state recovery, only concrete values. We will now explain a problem using a concrete example. So here we have a serialized execution which starts with register %8 equals to alloca stack allocation, stack variable allocation, then ends with an assert failure into a crash. So let's say we're trying to forward execute this. Well, let's say the core dump contains these values. Because we returned at position 4 here, the contents of the stack is lost. Therefore, everything is, well, unknown, denoted by the question mark. So here we first try to reverse execute, but since the addresses are unknown for the load and store, we just simply ignore them. Now we attempt to forward execute. However, since the return, the address for the stack allocation instruction is not concretized until compiled into machine code, remains unknown. This results in these two store and load instructions not being executed in repeat, resulting in everything being unknown, despite the fact that we can easily infer that 0 was stored and then loaded immediately. Therefore, register 104's value should be 0. And so here we present STRAB, which is an abbreviation of state recovery at abstract level. So our goal here is to increase the recovery rate of values in cases like shown in the earlier slide, while also minimizing the slowdown caused by the change in the reverse and forward execution algorithm. So we don't want symbolic executions. Our proposal is to use a hybrid memory location resolution and also some other techniques to help recover more values from the core dump and lifting them into IR level from machine level. First, the hybrid memory location resolution is, well, it's an hybrid of concrete and symbolic memory location. So it will treat, since LLVM IR is in SSA, we use the virtual registers as, well, symbols for memory locations if they are pointer types. That way, even if the addresses are unknown, we can still execute store and load operations. I will now show a more concrete example of that. So we return to the earlier example, and instead here we use our proposed hybrid memory location resolution. Here, because %8 is a symbolic, well, a hybrid symbolic location, we can now, STRAB will now execute store and load, treating %8 as a single memory location, resulting in 0, register 104's value being inferred as 0, which is much better than a simple extension of repeat. Now we look at I think there's another problem. Well, simply doing that isn't enough. Well, we still need to consider aliases. So for example, in a different execution path, let's say that %0 and registers %0 and %2 are aliases. Since our hybrid symbolic memory location the hybrid symbolic memory locations are well treated separately initially, as shown here. However, while forward executing, we will know that these two alias, therefore, we merge them during the inference of diffuse when creating the diffuse chain for a particular memory location, in this case 8080. So here we know that the value stored at position 3 is overwritten at position 6 to 2 because %0 and %2 alias. This way we can avoid, well, this is why it is a hybrid between concrete and symbolic memory locations. We will now move on to core dump lifting. So first of all, in order to reverse execute the program at IR level, we need to lift, so to say, the data values available in the core dump because they are still in machine level. So we use dwarf tree debug information to statically lift data values into the IR reverse executor. But that alone is not enough because for example, heap data values cannot be mapped using debug information, that is dwarf tree. So we also propose mid-execution lifting. So mid-execution lifting basically lifts values from the core dump during the reverse and forward execution. So it is separate from simply loading values via dwarf tree debug information. So here's a concrete example. Let's say that this instruction of position 2 is storing a value to some heap region. So we're reverse executing. So something was stored into the heap, but we don't know what that value was. However, since we know the address as 6090, we can load the value in the core dump. So the core dump says the value of heap memory 6090 is 5. So we can load the value on demand and lift it and infer that at position 2 the value 5 was stored, and therefore inferring that register %0's value is also 5. Now we will move on to experiments. Our goal here is to compare the performance of STRAB compared to repeat. There are two research questions. First, how much accurate is STRAB at IR level compared to a simple extension of repeat? That is for both, three of the proposals. So now, the second question is that how does STRAB affect the state recovery rate? Because surely it slows down because unlike repeat, we can do some extra steps to infer memory values. So we must measure how much it actually slows down. So here are now I will explain the methodology of the test. We use 4 setups and compare the recovery rate for these 4 setups. The base one is the simple application of repeat into IR. So we do basic lifting, the static one using dwarf3, but nothing else. The second setup is hybrid. We only enable the hybrid memory location resolution. The third setup is lift, where we enable the mid-execution lifting. And lastly, we enable the setting where we enable everything, which is our proposed method. Here are the test subjects. They are all real-world concurrent C programs. And also, most notably, we apply this to SQLite3, which is very big. Also, the other test subjects are from SAC'22 benchmark and some extra test subjects from previous work. So for the first research question, does the accuracy of recovered states improve? Well, the short answer is yes. On average, the correct values increased by 38%. And we gathered that the hybrid memory location resolution is effective regardless of test subject. However, the mid-execution lifting, as for the mid-execution lifting, they weren't always effective, but they increased the recovery rate in test subjects where they used a lot of heap memory. So here are the raw data, and as we can see here, the base into hybrid plus lift, we can see that on average 13%, the correct values have increased by 38% on average. And we can also observe that the lifting is only effective when the test subject uses a lot of malloc, aka heap memory. So here are the test subjects without, little malloc. However, the test subjects on the right side have a lot of malloc, therefore it's working. It's increasing the recovery rate. So now the next question, the second research question is how much does our new memory value inference algorithm slow down the recovery? So on average, it was 2.7 times slower than repeat. This may seem a lot, but repeat was already quite fast to begin with. Here are the related work. STRAB is part of a bigger goal of ours, which we have called SWORD, which is an abbreviation of software only reverse debugger. So the main difference here is that compared to other state-of-the-art debugging, concurrent program debugging methods, our method is hardware independent. So in conclusion, by proposing hybrid memory location resolution, cordon lifting, and mid-recovery lifting, we were able to achieve better accuracy and little slowdown compared to repeat. Thank you for listening.